as you introduced me, my name is Marjan, and I'm going to talk about a reusable recommender system that we built at Zalando for various fashion industry applications. So as you may know, Zalando is the largest European fashion retailer, but its mission is to also become a starting point for fashion inspiration. One of the ways this is done is through editorial content that consists of outfit and influencers experience, as well as algorithmic outfits to scale those experiences. Apart from content quality, one of the main drivers for engagement and customer retention at Zalando is definitely personalization. So some of this personalized outfit and influencer experience are the following. Get the look, which is basically an outfit, personalized outfit catalog and style carousel that contains personalized ranking that considers longer-term customer preferences. Then inspired by you carousel, which is an in-session personalized outfit recommendation carousels that contains outfit recommendations related to the current browsing session. Then we have you might also like, which is carousel related outfits that are also personalized and refer to the currently viewed outfit. And then when it comes to scaling these experiences, there is the algorithmic fashion companion that produces algorithmically generated outfits for recent purchased items so that the customer can inspire the customer for their last purchases or wish list items. And there is also influencer profile recommendation, which contains a carousel of related influencers on the influencer profile page. So historically, each of these customer touch points are served by different systems, which is trained on its own data, which is kind of understandable because each of them historically have been created in isolation. However, this results in a couple of issues for the organization. For example, increased complexity and maintenance cost. Then interaction with different entities along the customer journey, such as products or influencer, are not really effectively made use of. Basically, each recommender system is trained only on its own type of data. If it's the outfit recommender system, will be trained only on outfits. But there are other, as I said, entities on the customer journey, such as products, such as influence, that could be also relevant for the customer to predict the correct customer intent. Then only a subset of all customers on our platform actually interact with inspirational content, which means that we have the cold start problem also for customers that are already existing on the platform. And finally, user experience might vary from use case to use case because a different algorithm is serving all of these different products. So the question that we are ultimately want to give an answer in this talk is, can a single recommender system serve all of these use cases and at the same time with the baseline systems? So we provide some evidence from multiple live experiments that we have performed that a single transformer-based recommender system indeed can be reused across multiple related use cases. And we attribute this to three main things. First, the ability to train on diverse types of interactions. Second, the ability to encode session information. And third, the ability to encode contextual data such as current premise and a device, as well as other user attributes such as market, favorite brands, and so on. So other benefits of this approach include the following. We have now only one system to maintain, to extend, to develop, which is much cheaper for the organization. We have increased training size, set size. Indeed, whenever we train our recommender system only on the entity types for which this system is recommending, always results in worse performance compared if it's trained on all possible entity types in the customer journey. Then we have dampening of feedback loops thanks to interaction from various sources. And at the same time, the recommender system can address the cold start problem out of the box because we include these attributes, as I said, as contextual inputs and attributes that are about the customer itself, such as market, gender, device, premise, and so on. So this is the model training overview of the entire system that is trained on different item interaction, as I said. However, all of them are represented with embeddings of the same structure at the end. And we directly concatenate the temporal information and the interaction type so that the system is aware of also the type of information and the timestamp, which is coming to as which is an input to the transformer. And also we also introduced the concept of Boolean mask in order to consider only the items in the output that are relevant for the use case. So if we are recommending outfits, that we will only consider outfits, even though we are learning from different types of interactions. And depending on the target Boolean mask, right, we can adapt that Boolean mask to recommend whatever we would like to. So this is a typical click sequence in our scenario. The customer can begin with clicking on a product, then they can wishlist an outfit. Later, they can interact with an influencer and so on. So they're very widely, and to that end, we represent each of them with a set of items. Each of this set of items have two types of features. One of the types of features is actually referring to the products inside the set. As we can see here, the first product, it's a set of one item because it's just one product, and it does not have the features that are referring to the set itself. In this case, are empty. Where the second, in the second example, we have an outfit which consists of which is a set of the outfits this outfit consists of, but it also has additional attributes that refers only to the set, only for the set. In this case, that's the style and the influencer. On the other hand, the product doesn't have a style and influencer, and these features are padded with zeros. After averaging the values for the same features in the set, concatenating and padding those features that do not apply for the item, we get embeddings that have basically the same structure. And the first position, we always put the contextual embedding, which would also have the same size but contains different types of feature in order each of every other position to be able to attend to this to the first position. We also concatenate and one-code coding of the action types, so the model is also aware of the type of the action performed on the entity. As I mentioned, model insertion is also one of the keys to for effective recommender systems. User interaction, basically the interaction sequence consists of many sessions. And a session in this case would be a sequence of items within a limited time frame where the customer intent it's very clear compared to other session where the customer intent can vary widely. So if we ignore this information while making modeling decision, this can impact our model very negatively, which is also confirmed in our experiments. To that end, we model the session information, very simple but effective approach by introducing action recency embedding, which is concatenated to each of the items. This means that item with the same session will have the same action recency embedding, and items in the current session will always have an embedding that refers to one. And then the attention mechanism can choose which action is most relevant for the next prediction, depending whether the user is performing in-session browsing and we are providing in-session recommendation, or they're coming back to the platform after some couple of weeks, for example, after some time. So this is the model architecture for the recommendation use case. Here we see a classical encoder of the transformer, and this is the embedding layer, consists of action embedding, session embedding, and item embedding, and the context embedding, which is always in the first position. It's trained with casual language modeling, but we can also use other types of trainings. For example, we can also use we could also use masked language modeling would not really make a difference to our model. This is the model architecture for the outfit generation use case. So in addition, also contains a decoder, but it's trained on exactly the same sequence of items, with the only difference that we slice the sequences whenever there is an outfit, because the outfit it's the input to the decoder, which has the task to learn the fashion compatibility between the items in the outfit, condition on the output of the encoder, which has the task to learn the representation of the user itself. We see now the live experiments of the recommendation use case, which consists of 3 A/B tests performed on the 3 of the use cases that I presented before. The main observation is that for each of these use cases, we observe a very significant uplift in both retention and engagement, depending on the use case. Also, the baseline used, it can go up to 200% in our setting. Here we see similar live experiments for the outfit generation use case. We have performed 2 A/B tests against the existing system, which is based on Siamese networks. We have performed, as I said, 2 A/B tests. One of them is using fallbacks, and the other one without using fallbacks. So for this purpose, we develop a simplified, a more efficient version of the transformer for output generation that it's predicting embeddings instead of the entire set of assortment of items, which results in faster inference, but a little somewhat reduced quality. However, in both cases, we observe strong uplifts compared to the baselines in both retention and engagement. So these are some practical design choices. So we also, from the engineering point of view, come up with a flexible and configurable backend system that can be used through different use cases, thanks to this embedded configurable logic. In the interest of time, I will skip this slide, and I will focus on the scalability choices of our system, especially for the output generation use case, which is a little bit more challenging from the practical use case, and I'll explain the reasons why. So in a typical microservice architecture, in order to create a feature, our application service has to call external services to collect the data, in particular this item and entity data store, in order to create the features that in this case we see that are kind of duplicated. We have duplication of logic that it comes from the training pipeline and the serving applications. This is one of the inefficiencies. Another inefficiency is that in our use case we are working with sets, which means that this item entity data has to be called multiple times, and we put a lot of data on the wire, which is aggravated in our system, in our case, as I said, because we are generating outfits. And thanks to this, due to this autoregressive nature of the outfit generation, the application service had to wait on the model endpoint to generate the next item, which results in a very sequential process. So basically, in practice, such a system would be pretty unfeasible. So to address these issues, we make the following architectural choice. Basically, we merge the feature engineering inside the model endpoint, which now means we have a single code. The same code generates the feature for the training and for the serving pipeline. And secondly, we also move the item generation logic inside the endpoint, which means that the application service doesn't have to wait on the next item, but the entire outfit is generated in parallel inside the model endpoint. And finally, because so what I forgot to mention is actually that now we are not calling the item entity data store at all. Instead, we store a data dump of the item entity data inside a model endpoint, which means now that the entity data is a map in the computational graph in the endpoint. In terms of size, this is not a problem, because even for a couple of millions of items, the size does not exceed a couple of gigabytes. which is acceptable, at least in our use case. So now we put much less data on the wire. We use the same code for both training pipeline and application service to create the features. And finally, we generate the output inside the endpoint, which means that we can generate multiple outputs in parallel, thanks to the parallelization, the high efficient parallelization inside the TensorFlow graph. So that was all for this presentation. Thanks for your attention, and now I'm open to questions.
Thank you, Marjan. We have a few questions. For instance, do we consider user behavior at the same time window from the previous year instead of only tracking the latest behavior?
That's a very good question. In our experience, with experiment, we only consider user behavior up to 2 months, mostly because of GDPR and data privacy issues, but would not be a problem to consider even a longer period of user history data.
Okay, thank you. In the interest of time, please answer the questions in the Slido, and we're thanking Marjan again. Thank you.